GATE 2014 set 3 electrical question number 29. Norton's equivalent source in amperes as seen into the terminals X and Y is being asked. For this question you need to refer to NPTEL lecture number 53, Norton's theorem of the NPTEL course Network Analysis by Professor Taposh Kumar Bhattacharya, Department of Electrical Engineering, IIT Kharagpur. Norton's theorem states that any complex network like this, a black box arrangement. So this is some black box where you have some network which we don't know, and two output ports you see, and load is connected. Now what Norton's theorem is doing, this simplifying this complex network and replacing it with an equivalent source, current source I Norton, in parallel with Z Norton, that is impedance, equivalent impedance. Then you have same two terminals A and B after simplification, and then you can reconnect the load, same load ZL. So replaced with equivalent current source, as you see, Norton's current source I Norton, in parallel with Norton's equivalent resistance or impedance actually, as seen from load terminal. So this impedance can be calculated from this load terminal, then in parallel with the load ZL. Now the step is to open circuit the load first and calculate the short circuit current, from where you will determine this IN value. So IN is determined. After that Zn is determined by deactivating all the independent, passive, active sources by shorting the ideal voltage sources, since internal impedance of voltage sources, that is ideal voltage sources, are 0, and open circuiting the ideal current sources since they have infinite internal impedance. Now once you find the equivalent impedance from these two ports, as seen from these two ports, you are good to go with the implementation of Norton's theorem and simplification of the complex network by replacing it with IN and parallel with Zn, and then in parallel with the load connected at these two ports with respect to which the Norton implementation is done. Also, in any network, a voltage source V connected with an impedance Z in series across some nodes is equivalent to a current source in the same polarity that the current should flow. Let's say this is I, so this can be written as I, in parallel with this Z connected across same two nodes A and B, for example, where the relation is V equal to I into Z. Now with this useful information, we now try to find out the IN value across these two nodes for which the Norton's theorem was implemented. So I Norton value is found out by shorting the two nodes. So this is I Norton. In order to determine I Norton, this circuit should be simplified. So as I told you, 2.5 volts in series with 2.5 ohms is nothing but a 1 ampere current source connected in parallel 1 ohm across the two nodes. Coming to the solution, it is asked to determine the Norton current across these two nodes, for which Norton simplification will be done, and to do so these two nodes should be shorted, and the short circuit current of these two nodes is nothing but the Norton current. So in order to find the Norton current, this circuit should be simplified. Now let's break this voltage and impedance into current source in the same polarity, V by R, so 1 ampere, and connected in parallel with 5 ohms, and again we have 5 ohms and 2.5 ohms, and in series with 2.5 volts, and this is 5 ohm, and this is the network X and Y terminals. Now this is 1 ampere and this is 2.5, the parallel combination of these two, so 2.5 ohms, another 2.5, and you have this battery 2.5 volts. Now we have 5 ohms, again 1 ampere and 2.5. This can be converted back to a voltage source in series with a impedance. So IR, so 2.5 volts in series with 2.5 ohms, in series with 2.5 ohms, and we have 2.5 volts and 5 ohms. So this can be made equivalent to the Norton current is the short circuit current for these two nodes. So when you short these two nodes, this resistance goes out, and hence the Norton current is determined as 2.5 plus 2.5 volts divided by 2.5 plus 2.5 ohm equal to 1 ampere. So the answer is 1 ampere.